way I can have a separate list here. So we'll just take a little brief tour into models for moderation here. So here's my table of contents of where we're headed. First up is vocabulary. So what simply is moderation? An interaction term like this. That's it. So I have an X predictor, I have a Z predictor, and I have the two of them multiplied together with yet another slope in front of it. So beta 3 is called an interaction. In the old days, you had to literally create a new variable in your data set that would be X times Z, and that new variable would be entered in as a third predictor. In modern software, that step is no longer necessary, and you can fit interaction terms directly into your models without creating them. So in these kinds of analyses, the goal would be to ask, does the effect of X depend on where you are on Z? Like, is there a stronger relationship between X and Y for some people than others? But at the same time, you could also say the question is, does the relationship between Z and Y depend on where you are on X? It's two different perspectives, two sides of the same coin, so to speak, and either is valid. So which is the moderator in this combination is entirely an interpretation distinction, not a mathematical one. The way people talk about these is usually favoring one or the other. The moderator is like a dial that takes the slope you care about and turns it up or down. The slope you care about is called the predictor effect or the focal effect. So I will teach you to go back and forth. That way you have full capacity to interpret it whichever way you want. You can always test interaction terms in linear models, and this is also bad practice that I'm trying to unteach from years of folks learning things a certain way. So traditionally, if you learned analysis of variance, the default model in analysis of variance with multiple categorical predictors at the same time is to fit all possible interactions among them. Like if you fit that in SPSS, that's what it does for you without you telling it that. Interestingly, even though not all of the interactions may be significant, people usually interpret the results keeping everything in. I don't know why, but that's just dogma. If you have ANCOVA as your analysis strategy, the C that differentiates it from ANOVA is for a covariate. Covariate is a term that means a numeric predictor. And in this type of model, they have strict rules about what your numeric predictor can do, and it can only have a main effect. It can't be included as part of your interactions. Otherwise, you've violated homogeneity of regression. Bad. Well, then just don't call it ANCOVA, and you're fine. You can fit whatever you want. It's an artificial distinction. If you're doing regression, so if all of your predictors are numbers rather than kinds, there is no default strategy. It's whatever you say it is. So you would have to think critically about which interactions you would have a reason to expect and you would want to fit into your model. So I think part of the issue in how folks have been taught how to address questions about moderation is tied to this sort of dogmatic way of thinking about what's allowed. And what I still see folks do in practice is take a numeric variable and cut it up to put it in an interaction term. Have you seen this? It's called a median split a lot of the times if it's a cut of 2. And other times they might cut it up into low, medium, high so that you can then say the slope is this in the low group, the slope is this in the medium group, and the slope is this in the high group. You don't have to cut up a variable, and neither should you. Cutting up a continuous variable introduces measurement error for no reason, and there's a long literature on why not to do that. So we will keep the variables as they are. From our perspective, it doesn't matter if X is binary or X is one contrast within a nominal variable, that would be binary, or numeric or whatever. We can examine any kind of interaction terms that we want to. The rules are, though, that we have to keep beta 1 and beta 2. So this is where you're going to start to hear a change in terminology that comes about once you have models with interaction terms. Beta 1 here and beta 2 are going to be called main effects. Are these terms you've heard before? Maybe? You have? It's like in ANOVA world, right? You have your main effect, you have your cell mean, your marginal mean, your interaction mean. Yeah, these are main effects, meaning just x by itself, just z by itself. So in order for x and z to represent an interaction, it has to be above and beyond the main effects in that case. The trick is to identify what the interaction is doing and to recognize that its role in the model is not to predict y. Its role in the model is to predict each of the slopes that then predicts y. So let me go back to the equation here. Here's a common thing that I hear folks do when they're writing interaction terms up. They would say beta 1 is the effect of x, beta 2 is the effect of z, and beta 3 is the effect when both x and z are high. That language doesn't work. What's going to happen is that beta 3 is going to change what beta 2 becomes as a function of x. Beta 3 is going to change what beta 1 becomes as a function of z. So interaction terms change the slopes, slopes change the predicted value. That's the hierarchy here. And there's only four possible kinds, and maybe even only two. So there's 4 patterns that I'll teach you to recognize, and once you figure out which pattern you're in, you're home free. So this is a different type of conditionality than what we've seen before. In models with multiple predictors, we talk about how each of these is the unique effect, right? So like beta 1 is the unique effect of x after controlling for z, beta 2 is the unique effect of z after controlling for x. Except x and z are also in here too. So what's going to happen is, in order to talk about this as the effect of x, I have to adjust for this missing piece right here. So beta 1 is only the effect of x when z goes to 0. If z is 0, this entire piece here in the box goes away, and then beta 1 is all the effect of x. Likewise, beta 2 is only the effect of z by itself if x is 0 and this thing goes away. So what's going to end up happening is that beta 1 and beta 2 aren't just controlling for the other variable. They are specific to the other variable being 0. So x here, this is the, beta 1 is the slope of x when z is 0. Beta 2 is the slope of z when x is 0. And then beta 3 talks about how those slopes go up and down as a function of the other variable. That's how moderation is going to work. All right, back on here. I think I'm deciding the order in which I'm thinking of changing it up, potentially, because the terminology is a little bit chaotic. Let's go to here. Slide 6, we're going to do a little play along. And by the way, I will post the finished version of this when we're all done with it, but I'm going to start typing. I'm going to skip ahead to slide 6 here. There's only 4 kinds of interactions in the world. And actually, you can boil those 4 down into 2. The rest of it is a semantic distinction. The role of an interaction is to take the main effect slopes and make them either more positive or more negative, if the interaction is strengthening the effect of that predictor, or it will take the main effect slopes and make them less negative or less positive if it is weakening the effect. So let's throw some numbers on this and talk about what happens. Let's say that in this equation here, I have W here as a main effect, so it's not interacting with anything, so it's not going to be part of our story on this page. I've got the main effect of x, the main effect of z, and the interaction. So if beta 2 were 10, right here, that's 10. Let's say that beta 4 for the interaction was a positive 2. The way that I would talk about this is that for every 1 unit higher x is, y goes up by 10 if you're talking about z of 0. That slope of 10 becomes, this one is a more positive combination, because For every unit higher z, what's going to happen is the slope for x gets cranked up by 2. So it's 10 to start with. If z goes to 1, it goes to 12. If z goes to 2, it goes to 14. So it's taking that slope of x and cranking it up as a function of z. So these two numbers are in the same direction, so they work together. Does that sound familiar? Like if the signs are the same, then it's more, and if the signs are different, then it's less. See, you already learned this. I just called it quadratics last time. But if you think about x and x squared is x times x. It's an interaction. So the rules are the same. So the first scenario, if the signs are the same, what we would say is that as the moderator z increases, the positive effect of x becomes more positive by 2 per unit. This one, slope of x is still 10 to start with. Interaction term is negative. So this would be, any guesses? Yeah, this is a less positive. Because what happens is this slope is 10 if z is 0. As z goes to 1, it would be 8. As z goes to 2, it would be 6. So you're taking a positive slope and turning it off. What if the slope were negative to start with and the interaction were negative? Which one is that? More negative. So the negative slope of negative 10 would become negative 12, then negative 14, then negative 16. So this way. Last but not least, negative slope, positive interaction. That's negative. Yeah. So now the negative slope is weakening towards 0 as z increases. So these two and these two, number 1 and number 3, it won't let me do both at the same time. Those are the same idea. That's taking a slope and making it stronger as the moderator increases. What stronger means depends on the sign. So that's where more positive and more negative are different ways that the slope can become stronger. It's moving away from 0 in 2 different directions. Likewise, 2 and 4, those are examples of slopes that are becoming weaker as the moderator increases. They're getting closer to 0. So the language that I tend to use in talking about these kinds of things is matters more, matters less. So x matters in predicting y, but maybe x matters more if you're high on z, or it matters less if you're high on z. So the key idea is that the interaction terms are changing the slopes of the other variables. They are not directly changing y. If you can hang on to that, we're good to go. And this is what your last homework will be. Getting practice with interactions. But it's not due for like a month, so it doesn't exist in your mind yet. It's fine. It's in my mind, because I got to get folks who, I got to get it to the TA so you can practice with it. Soon, this week, I hope. All right, I just wanted to give you a little bit of a taste of this, but I have terminology to go through and an example to go through, and then we'll go through our usual database example with syntax and output and stuff, and that'll take the next several classes, I think. Had enough for today? I think we have. I think I have. That's fair. It is 3:07. I made it most of the way. Things you want to ask about or hear more about before we adjourn. Page 2. So in terms of what not to say or what I would say? What I would say. Okay. The way that I think about this is that the job of beta 3 is to adjust beta 1 and beta 2 as a function of the other variable. So beta 1 changes as a function of z by that much. Beta 2 changes as a function of x by that much. So you talk about the interaction as what it does to the main effect slopes. You can then talk about the main effect slopes as what it does to the predicted outcome. All right, others? Okay, then thanks for being here. I know it's not an easy point to make time for class, and I appreciate it. Let us know if we can help you. Office hours as usual, and homework 4 due next week. Okay, bye for now.